You know, for the longest time, we've just kind of accepted that AI reasoning is, well, it's a guess. A really, really smart statistical guess, sure, but a guess nonetheless. But what if we could change that? What if we could swap out that guess for cold, hard mathematical proof? Today, we are diving into a huge shift in AI, one that moves us away from just approximating and toward absolute certainty. Okay, let's just get right into it. Because this is the question, isn't it? It's the one that's keeping people up at night as we start handing over really high-stakes decisions, in medicine, finance, even law. In those fields, close enough is absolutely not good enough. Understanding how an AI thinks suddenly stops being a nice-to-have and becomes completely critical.
In this image, it just perfectly captures what we're talking about. On one side, you've got current generative AI. It's like a lottery machine, right? It's just pulling a statistically likely answer from this big spinning drum of possibilities. But on the other side, you have the semiotic web, which is more like a GPS, navigating a known map to a very precise verifiable destination. This is the journey from randomness to rock-solid certainty.
So this leads us right into the first big hurdle, the black box dilemma. It's simple, really. We can't trust what we can't understand. And right now, pretty much all AI thinking is happening inside a box that we just can't fully open.
See, these AI models, they don't think in words or pictures like we do. They operate in this unbelievably complex internal language. Think of it like a geometric map with millions of dimensions. And to be super efficient, a single point on that map can represent tons of different overlapping ideas all at once. That's a concept called superposition. Now, this makes the AI incredibly powerful, but for us, trying to peer inside, it makes its reasoning almost impossible to untangle.
So for years, the entire field of AI interpretability has been obsessed with trying to translate that internal language. And it really all came down to cracking one single core mathematical formula.
And here it is. Y is approximately equal to D times X. Now, the best way to wrap your head around this is with a baking analogy. Think of Y as the finished cake, the complex thing the AI gives you. The goal has always been to figure out D, which is like the pantry of pure ingredients, flour, sugar, eggs, and X, the recipe card that tells you exactly which ingredients were used and how much. We've been trying to break the cake back down into its simple, basic parts.
But here's where it gets wild. Researchers threw everything they had at this problem. On one side, you've got the new school stuff, neural networks called sparse autoencoders. On the other, you have old school rigorous math algorithms. And even though they are philosophically complete opposites, they both slammed into the exact same performance ceiling. They got stuck. And the crucial takeaway here is the problem wasn't the tools. The problem was the formula itself. We were all trapped inside a mathematical cage.
So if your best tools can't break through the wall, what do? Well, you've got to change the problem itself. And this is where the big paradigm shift happens. Someone proposes to change the very formula that everyone has been trying to solve for years.
This formula right here, this is the world we've been living in. A world of close enough. That little squiggly line, the tilde, that's the mathematical ceiling we were just talking about. It's the source of all the fog, all the ambiguity. It's literally the guess.
And then there's this. The proposal is to just get rid of that squiggly line and replace it with a hard equal sign. Now, it looks so simple, but the implications are just absolutely massive. We are literally talking about moving from a world of statistical guessing to a world of mathematical proof.
This table just breaks down the entire shift beautifully, from approximation to perfection. Just look at the row for the data, for example. In the old world, the output is this complex whole, but where it came from is murky. In the new world of semiotic comprehension, every single dimension is explicitly built from real-world, validated semantic atoms. We go from guesswork about the recipe to a fully auditable ingredient list. It's a total transformation from a black box to a glass box.
But how is that even possible? I mean, you can't just change a symbol and call it a day, right? This isn't just some theoretical tweak. There's a proposed framework called the semiotic web that introduces a complete architectural breakthrough, and it's all centered on an algorithm called the Tokumizer.
Okay, so the Tokumizer rebuilds meaning from the ground up on this super stable foundation called semantic DNA. It's a four-step process. First, ingestion. It only takes in data from trusted, whitelisted sources in a really simple, structured way. Second, validation. That data has to pass these strict constraints, making sure its meaning is stable and reliable. Third, atomization. It breaks the data down into these unchangeable atoms of meaning. And finally, molecule creation. It combines these verifiable atoms into more complex molecules of knowledge. Every single piece is locked, traced, and totally unambiguous right from the start.
So here's the difference in a nutshell. Generative AI samples data, squishes it down, and then makes a probabilistic best guess. And every single one of those steps adds another layer of approximation. In contrast, the semiotic web starts with all the available data, creates a complete inventory of knowledge units, and then gives a deterministic grounded answer. There are simply no guesses anywhere in the chain.
So let's zoom out a little. What does all of this actually mean in the real world? If we can pull this off, it fundamentally changes what an AI is, and way more importantly, what we can actually trust it to do.
This slide just puts it side by side perfectly. Generative AI is built on probabilistic guessing from partial data. The semiotic web is built on deterministic navigation of a complete inventory of knowledge. It is, quite simply, the difference between an educated guess and grounded truth.
I think this quote from the research just nails it. It's a move from statistical approximations to deterministic semantic algebra. I mean, just think about that for a second. Meaning isn't estimated anymore. It is calculated with the kind of precision you see in algebra.
So the whole point is this. We're going from an AI that makes these unbelievably sophisticated guesses to one whose reasoning is verifiable and completely known. It's the difference between asking an AI to guess the recipe for a cake and having it hand you a cryptographically signed exact list of every single ingredient and every single step. And this isn't just a cool technical achievement. It unlocks a future where we can finally apply AI to our most critical problems with real confidence.
Oh, and there are huge practical benefits too. Because this approach builds knowledge instead of guessing it through endless trial and error, it could reduce the need for that traditional, super energy-intensive training and fine-tuning by a staggering 96%. This makes truly trustworthy AI vastly more efficient and accessible.
And that leaves us with one last massive question to think about. If we can actually build an AI whose thoughts are no longer a black box, but a transparent mathematical proof, what are the big, world-changing problems that we can finally and truly trust it to help us solve?